should be very comfortable with. Also, time shifting, you should be comfortable with. Also, another thing that's important, and you probably see on the midterm, because on the final, because some of you were struggling with on the midterm, is periodic signals. Okay, I want you to be able to give me the period, the fundamental period, the fundamental frequency in hertz and radians per second. Okay, so that's one of the questions that I thought it was very easy and it was on the midterm, but some of you could not get the correct answer. So that's why you're going to see that again in the final. So I hope that's clear enough. And systems, okay? Systems are again important, and regarding systems, I want you to know the classification of systems. Again, this is something that a lot of people struggle with, so we're probably going to see something like that in the midterm. And interconnection of systems, so that's when you have a bunch of systems interconnected with each other. That's another thing I want you to know. And that's about it. So these are the stuff that I want you to know regarding signals and systems. And then we learned about linear time invariant systems. This is the special type of systems that we consider, that where the system is linear and time invariant. Okay? And for these ones, we said that the impulse response is basically the output of the system when the input is the unit impulse. Okay? So when the input is the unit impulse, the output would be, we call it impulse response. Okay? And we said it's important because it basically, for any input, you can get the output by convolving the input with the impulse response. Okay? And so that's basically where convolution comes in. And you should be able to answer these questions by yourself. You should be able to explain this for yourself, basically. If somebody asks you what is impulse response, why is it important, you should be able to answer this on your own. Okay? And yeah. Yes. Yeah, short answer questions. I mean, so these are not, I mean, I don't want you to do any kind of crazy convolution integral, okay? I mean, you didn't see something like that in the midterm, you're not going to see something like that on the final, okay? So, but from convolutions, what I want you to know, and I went through this to some extent in Monday's review, I want you to know the convolution of the unit impulse. When you have a convolution with the unit impulse, and we did this yesterday as well. Okay, I want you to know that. So these are the special properties of convolution. Also convolution with unit step. So these are the type of questions that I could give you on convolution, because convolution integral itself is very difficult. I'm not going to give you that. But convolution with the unit impulse, it's easy. You just have to shift the signal by the amount that your unit impulse is shifted. With unit step, it becomes an easy integration, easier than the convolution at least. And you have to also be able to take care of the time shifting, you know. Yesterday we saw the example where the delta functions were time shifted, and that resulted in shifting the signal. Okay, so these are the basically the three important properties that you should definitely be comfortable with. The rest of the properties are also important, but these are the three most important ones that I want you to be very comfortable. Okay, and generally just know what is the inverse of the system. Okay, and so that's basically the stuff that I want you to know from the material before the midterm. And then basically for the rest of the course, what we said was that the convolution integral is difficult. Can we do anything better? And then we started introducing Fourier series, Fourier transform, in order to do the convolution in an easier technical manner. So I'll stop here and I'll go to the Fourier series. I'll go to Fourier series lectures and I'll start from there. I think lecture 12 was the first one. Lecture 12 is the first one.
Oh, it looks so weird.
So, like I said, what we did was we introduced in the first half the signals and systems, then we introduced a special type of system where you have, like I said, the impulse response, which is the output when the input is the delta function. And then we said that we have this convolution integral, which we have here, which gives you the output, if you know the input and the impulse response. Okay? And then we said, can we do anything better? We said, okay, the convolution integral is difficult, and let's see if we can do any better. And we said, okay, let's observe what happens to this linear time invariant system when the input is this special function, which is a complex exponential function. Okay, which we know it's periodic from chapter 1 or from basically signals. We know that the complex exponential is periodic, and it has 3 basically parts. One is the amplitude or the magnitude. The other one is the frequency, fundamental frequency, and it has a phase. Okay, it's like a sinusoidal function basically. And for simplicity, we said let's assume the phase is 0. Okay, and therefore it has an amplitude, the function has an amplitude, and it has a frequency. Okay, and the phase is 0. And we said, okay, what happens when this is the input to the linear time invariant system? What output does the system produce? And then we went into doing some math, and the math turned out to be a bit, I guess, messy. That's why I'm not going to bother with it anymore. But no, these parts are basically the derivation, and I wanted to show you how we get from this input to the output. That's basically the proof of going from the input to the output. And the way we did it, we actually carried out the convolution integral, and we simplified things. And basically, the important slide here is this one. Okay, so by doing all of those calculations, we showed that when our input signal is this function, which is a sinusoidal, or these two functions, the output turns out to be also a sinusoidal as well. Okay, the output turns out to be the sinusoidal as well, and the only thing that changes is the amplitudes and this phase. The frequency remains the same, the amplitude changes, and there is this phase that changes. So that's the effect that the linear time invariant system has on sinusoidal functions. Okay, which is better than doing the convolution integral when you have these special functions. The only things that change is the amplitude and the phase. Okay, and we said, okay, this is good, but can we represent signals as a summation of these complex exponentials? Okay, because if we can, then on the other side, the output that we get is basically the summation of these new exponentials, which has only the amplitude changes and the phase changes here. Okay, and so we went through all of these, basically showing that in fact we can. Okay, if x of t is periodic. So we showed that if x of t is periodic, we can write it as a summation of these complex exponentials, and we called it Fourier series. Okay, and we called it exponential Fourier series, which is basically this guy. And these d of n's, we call the Fourier series coefficients. Okay, we call these the Fourier series coefficients, and we said you can calculate these Fourier series coefficients using this integral. Okay, and which, as you can see, this integral is much simpler than the convolution integral, because convolution integral is just a mess. Okay, so what else do we have here? And we said, okay, these complex exponentials, these Fourier series coefficients, we said they are a function of this n omega naught, which is the frequency, and also their complex value. Okay, and also their complex value. We also showed that there's another form of this Fourier series, which is in terms of, instead of having the complex exponential, it is in terms of a cosine and a sine function. And again, the coefficients here become the a sub n, 0, a sub n, and b sub n. Okay, and this form, we said it's better because it tells us that you can write a periodic signal. Remember, here for all of these, the x of t is periodic. We said that the x of t, when it's periodic, you can write it as a summation of a bunch of cosines and sines, which are harmonically related. Harmonically related means that you have this base frequency omega naught, and you have the integer multiples of these omega naughts, okay? And for all of them. That's what we mean by harmonically related, okay? And so we said this form basically is good to show the meaning, and the other form, the complex exponential, is good when we do calculations. And basically by meaning, we mean this. If we draw the first harmonic for this square periodic signal, you can see that the curve is nothing like the square. But as we go to higher harmonics and we add them up, the red curve, which is the addition of all of these sines and cosines, becomes much more similar to the square wave. And eventually, as n approaches infinity, it becomes the same. Okay, and this was another demonstration where you have a sawtooth or triangular wave, and you can see as you increase the harmonics and you add them, the series becomes almost like the function itself. Okay, so, and these were basically the summary of all of the things that I just said. And the other thing that I want you to be comfortable with are these basically coefficients. Okay, so we said if we know these coefficients, we can just substitute them into this formula, and we can get x of t. Okay, because if we know all of these coefficients, all of these a sub zeros, n sub 0, a sub n, and b sub n's, we can just substitute them in this formula, and when you do this summation, we get x of t. Okay, and we said there are two forms of coefficients: the trigonometric and the exponential. Okay, and they're related by this formula. Okay, and so keep in mind when I gave you the assignment, you only had one assignment on Fourier series and Fourier transform, right? And that one assignment, there was basically one question on Fourier series. So that should basically tell you the question you're going to see on the final on Fourier series. Okay? Yes. X of t was equal to basically 5 plus 5 cosine of 5 pi by 3 t, okay, plus or actually minus 7. What was the rest? Cosine of 4 pi by 3 t, okay, and minus 3, okay, sine of 15 pi by 9 t. Okay? So basically when you look at this, okay, how many terms do you have which are without a sine or a cosine? Which depend on t, of course. I mean, 1, right? So this would be your a sub 0. Okay, but before you can do that, you have to find also show that this thing is periodic, because x of t should be periodic so that you can write it as a Fourier series. I might change these numbers. Actually, can I do that? Yeah, I might be able to change these numbers such that x of t is not periodic. Okay, so first thing you need to do always when you see a question like this, you have to show that it's periodic. And basically the first part of question takes care of that. The first thing that the question asks you is that find the fundamental angular frequency of this x of t. Okay? Once you find that, you essentially have shown that the signal is periodic. Okay? And once the signal is periodic, you isolate this term, okay? And this becomes your a sub 0, n, 0. Okay? So a sub 0 is always easy. It's this term. The term that's without these t's. Okay, and if you look at the formula, that's basically a sub 0. Okay, now the next one is how many cosine terms do I have? 2. So therefore, I should have 2 a sub n's. I should have 2 of them that are non-zero. The rest are 0 basically. Okay, so the first one would be at. So for this particular signal. The fundamental frequency, I believe, is pi over 3.
Yes.
Yeah. The fundamental period is pi over 3. Okay. And you have to do calculations to show that, but I'll show you an easy way, but you can't do this on the final, okay? But you can do this to check your answers. The way you can do it is by basically you try to find the common factor between all three, okay? And the common factor you find between all these three is pi over 3, okay? And therefore, the fundamental period is pi over 3. So, how many multiples of pi over 3 you see here?
1.
5, right?
Yeah.
Right? So at n equal to 5, okay, the value of my a sub n is basically 5. So at n equal to 5, the value of a sub n is 5. At n equal to 4, what is the value?
4.
Negative 7. Okay, be careful about the negative. And at so it will be 0 otherwise. Okay, it will be 0 for all other n's, right? Because there is no other a sub n, there's no other cosine term. That's left, right? Because there's no more cosine term. And keep in mind, this is the summation. Okay, this is the summation. We're summing all over all these cosines. Okay, so in essence, you have two a sub n's that are non-zero, and the rest are 0. So technically, you have infinitely many a sub n's. It's just that 2 of them are non-zero. The rest are basically 0. Okay. Same thing is for b sub n. Okay. For b sub n, you look at the sign terms. How many sign terms do you have? 1. So you're going to have only 1 non-zero. And what's the multiple of? What is the multiple here? I mean, multiple of pi over 3. What multiple of pi over 3 is this?
5.
5, right? So at n equal to 5, the value that you have for your b sub n is negative 3. And it will be 0 otherwise, because you don't have any other terms. Okay? So this will give you, basically, the trigonometric Fourier series coefficients, all of them. We have infinitely many a sub n's, infinitely many b sub n's, and 1 a sub 0. Okay? And the second part asks you for the exponential Fourier series coefficients, which you can basically solve using this formula. Okay? So because we already calculated all these a sub 0s, a sub n's, b sub n's, and just subbing in for this formula, we can calculate these exponential Fourier series coefficients. Okay? So any questions here?
I'd love to see an example again of how to get the D event coefficients.
Sure. I'll do it here. So, what did we calculate? We calculated those. Okay. So, basically the way we do D sub n is like this. At 0, at n equal to 0, it's the easiest. Okay, at n equal to 0, according to this formula, it's equal to a sub 0. So what is the value of a sub 0 we calculated? 5, right? So the easiest one is this one, we just sub in 5. Okay? Now the tricky part are these non-zero ones. Okay? And for each non-zero n that you see, okay, how many non-zero n's do we have here? 3. But 2 of them are the same. The 5s are the same. Right? So in total we have 2 distinct versions of n's that are non-zero. Right? 4 and 5. Okay, because 5 repeats here. So for each of those you have to have n equal to 5 and n equal to negative 5 and n equal to 4 and n equal to negative 4. Okay? So for each of the non-zero n's, okay, you have a positive version and a negative version, a positive version and a negative version, okay, for each of those. Now, from the formula, let's do this 4 first. Okay, let's do 4 first. What is a sub 4? It's the value is negative 7, right? What about B sub 4?
0.
0, right? Because we don't have it. It's 0 otherwise. It's only at 5 that it's not 0. So at n equal to 4, we get 7 over 2. Okay? So let me just leave enough space. That would be n equal to negative 5, n equal to 4, n equal to... Okay, so at negative, it's negative 7 over 2. Right? Because there is this factor of half. Okay? What about at negative 4? At negative 4, we have to look at this formula. Again, a of negative 4 would become a of 4. Right? Because I have a negative and I'm looking at n equal to negative 4. So a of negative 4 would be a of 4. Okay? And a of 4 is again negative 7. Okay? Do I have a b of negative 4, which is b of 4? No, again, b of 4 is 0. So we have, according to formula, negative 7 over 2 also for this case. Okay? Now, let's do 5. Okay, let's do 5. For 5, we have to look here because it's positive. What is the value of a sub 4? A sub 5? A sub 5 is 5, right? And also, what is the value of b sub 5? Negative 3, right? And because of this negative, it has to become positive, right? So I have, for this one, I have 5 over 2, right? Because I have to divide everything by 2 because of that factor of half, plus 3 over 2 I, or j, doesn't matter. Okay? And now let's do the negative 5. The negative 5, we have to look here. What is the a of negative 5, which is a of 5? It's again 5. And so let's write that one, 5 over 2. And the other one would turn out to be negative 3 over 12. Okay, because it would be b of negative 5, which is negative 3. So you sub in negative 3, it would be negative 3 over 12. Okay? And that's it. It would be 0 otherwise, basically. Because all the other a's and b's are 0. Okay? So, like, this was a case where you had 3. Things might become a bit more tricky. And so it's important to distinguish the terms that are a function of t and the terms that are not, they're constants. Okay, so here 5 is constant, the cosine is a function of t, the cosine is a function of t, the sine is the function of t. So it's important to distinguish those. Okay, so that's that, and any other question actually on this while we're here?
So this is like going to be 40% of the exam?
Not this particular question.
So which particular question is it?
The particular question you'll see on the final, but then no question is both 40%. But like I said, Fourier series and Fourier transform together they will be 40% of the final, of the final exam, of the whole final exam. Yeah, because 40% would be this, 40% would be probability roughly, and these are like rough. And 20% would be before the midterm, like material from the midterm and before.
For this particular question,
Yeah.
why is it that you said I?
It's because of the formula. I mean, the formula has a j, but j and I are basically the same.
The other one is 0. Okay.
Yeah. Yeah, exactly. Okay, any other questions? Let's move on then. So that's these are the stuff that we see. The other important thing that we mentioned is that basically if we know these coefficients, like I said, these coefficients, I could write the summation and get my signal x. So knowing the coefficients is equivalent to knowing the signal x. Okay, that's the alternative Fourier series, and that's basically the frequency domain representation. The frequency domain representation are these coefficients basically. Okay, because if we know them, we can recreate the signal using the summation. And then we talked about the Fourier spectrum and said because these coefficients, if we know them, if we know these coefficients, we can recreate the signal. So for example, if I have a signal g of t, and it's given by these Fourier series coefficients. Okay? If I sub in these coefficients into my summation and calculate the summation, I'll get back this signal. Okay? And because of that, this is an alternative view of the same signal in frequency domain, because this is a function of frequency. Okay? This is a function of frequency. And as an example, we showed that if we use those frequency signals, these Fourier series coefficients, because they're complex valued, okay, you have to use the magnitude spectrum, which is the magnitude of this complex number, which looks like that, and the phase spectrum. Okay? So this was a question actually in your midterm. What is the magnitude spectrum and what is the phase spectrum? And that's basically what they are. Because those coefficients are complex, we can't use one plot to show them. We have to use two plots, and we use the magnitude and the phase, which basically is the argument. Yes?
We won't actually have to like graph it or anything, will we?
You sorry?
We won't actually have to graph it or anything?
No, no.
Any graph?
Yeah, there will be some graphing questions, but
Like what?
similar to the ones that I talked about yesterday. So there will be some graphing questions similar to the ones that I talked yesterday. So let's see. Also, there were some more examples. So this signal, you can convert it into basically its magnitude and phase spectrum that look like these, and so these are basically the magnitude and phase spectrum. So, and this is the summary of all these concepts. So for Fourier series, we have these two domains, the frequency domain and the time domain, and we can use the formulas to go from one domain to another. The time domain is always real valued. The frequency domain might be complex valued. Okay, and therefore we have to have the magnitude and the phase. The time domain is always, in these cases, is continuous. The frequency domain is discrete. Okay, the frequency domain is discrete for Fourier series, which talks about periodics. Okay, and these are the formulas to go from one domain to another. So here you can go from time domain to frequency domain using this integral, and over there using the summation, you can go from frequency domain to time domain. Okay, and so that's basically, I guess. And there's some properties of Fourier series, which I'll go over with Fourier basically transform. I'll go over those properties when I talk about Fourier transform. So these are the stuff from Fourier series, and let's do lecture. I'm going to jump to lecture 15 actually. Do you want me to go over lecture 13 and 14?
There's not an exam.
No.
I don't know. Actually, I don't know. There might be something in it that might be in the exam. But I'll go to lecture 15 because it summarizes all of those. But you can go over lecture 13 and 14 on your own. And basically, lecture 13 and 14 are those. Lecture 13 is basically Fourier. Let me see what they are. Lecture 13 is Fourier transform, the way I introduced it, and lecture 14 was that weird way of representing Fourier series and Fourier transform using those devices that we built. Okay? Yeah, so that's lecture 14. I don't know whether that worked out or not, but...
rebuilt devices.
Sorry?
You weren't there when I made them?
Huh?
You weren't there?
Yeah, anyways...
I think I was. I just don't remember.
Okay, so this is basically the review of the same concept. So I'm going to go to lecture 15 because I think that would be more productive. I'm going to go to lecture 15. 15, and you can review lecture 13 and 14 on your own and ask me questions on Wednesday.
Could you see the screen?
So for lecture 15, basically by now we've represented the so again, a review of harmonics. So for those of you who don't know what a harmonic is still, if you have some base frequency omega naught, okay, the mth harmonic is basically the integer m divided by that frequency. So for example, the second harmonic is 2 omega naught, the third harmonic is 3 omega naught, and so on. Okay, so if this is my base signal, okay, and the base frequency here is 2 pi. Okay, the second harmonic would be 4 pi. The third harmonic would be 6 pi. Okay, and so on. The fourth harmonic would be 8 pi, and so on. Okay, and basically by increasing the frequency, by multiplying the frequency as the harmonic number increases, you have more frequency within the same period. Okay, so here, for example, you can see there is one within one time unit, there is one period, and here within that one time interval there are 2 periods. Okay, so by going to the second harmonic, you increase the number of periods. Now, so these are basically the summary of Fourier series. So this is the stuff that I talked about. So you're good. But also this is an important table, okay? This is a very important table, and it basically summarizes some of the properties of the Fourier transform, okay? And this linearity property is very important. The time shifting property, it's very important. Time shifting and frequency shifting both are important, but time shifting more so than the frequency shifting. And the integration and differentiation, don't worry about those, but the time convolution and frequency convolution are also important. Okay, and you will be given a table of I'm going to give you this table on the final. I posted already what I'm going to give you on the final, so you already know that you'll get this. So out of these, like I said again, linearity is important, time shifting, frequency shifting important, and also the two convolutions are important. And yesterday, actually, the problem that I solved uses the frequency convolution. Okay, where we were multiplying our signal with the carrier frequency in the time domain, and we saw that you can use the convolution to represent them in the frequency domain. Okay, and that was the amplitude modulation. So make sure you know how to use this table and you're comfortable with it. And there are actually, in the practice question for assignment 6, there are some examples of how I use this table. Okay, and also in the example that I did on Monday, I'll use this property. Okay. Also, this other table you'll get, okay, which is the Fourier transform pairs, and you can see like for all of these functions, you'll get all these pairs. The only thing that it doesn't have the plots, okay? The table that I gave you doesn't have the plots, but you don't need the plots, okay? And as long as you know how to plot the delta function or simple functions that you already know, the unit step and stuff like that, the sines and cosines, the stuff that you've already seen, okay? You're good. I mean, I don't want you to draw like something like this or that. Okay? So this table will also be given to you, so you don't have to memorize it. And I guess that's that. What was in lecture 14? I'm going to probably cover the end of lecture 14 as well.
It's not working. So slow.
So this is another thing I want you to know, the Fourier series versus Fourier transform. Okay, I want you to know the difference between these. Okay, the difference between Fourier series and Fourier transform.
This
So, Fourier series works for periodic signals only. Okay, Fourier transform works for both periodic and aperiodic. Okay, when you use Fourier series to go to frequency domain, the frequency domain representation in Fourier series is discrete. Okay, the frequency domain representation is continuous for Fourier transform. Okay, so that's like two differences, and then there are also the differences in formula. So this is the formula for one, this is the formula for another one, and these are the formula for the Fourier transform. And you can see the summation becomes integration when you go to Fourier transform. And so these are the two important differences of the Fourier series Fourier transform. This is another important, again, concept. So we said, so our quest was basically the reason we introduced Fourier series Fourier transform. It turns out to be the Fourier series and Fourier transform are actually much more useful than just linear time invariant systems. But in linear time invariant system, they're useful at doing calculations without doing the convolution integral. Okay, so avoiding convolution integral basically. And the way we do it is that if we use the Fourier transform, which works for both for continuous, both for periodic and aperiodic signals, we can convert our input into frequency domain from time domain, and also we could convert our signal y of t output signal to the frequency domain. Okay, and we could also convert our impulse response, okay, to frequency domain. And when we do that, the name becomes the transfer function or frequency response. Okay, so you should know what frequency response or transfer function is. Okay. And that's basically when you convert your impulse response into frequency domain. And this is the time domain representation of how this input signal x of t, the input signal x of t, the impulse response, and the output signal y of t are related. And you can see they're related using the convolution integral in time domain. But when you go to the frequency domain, they're related using this multiplication. Basically, the input signal in frequency domain, you multiply it with your impulse frequency response, and it becomes your output in frequency domain. So the convolution becomes a multiplication. Okay, the convolution becomes a multiplication, and why is this important? Actually, for your assignment 6 again, and the practice questions there, what you did, the first question you did Fourier series, the rest you did Fourier transform. And the questions involving Fourier transform involved linear time invariant systems. Okay, so I want you to know these two pictures of time domain and frequency domain involving linear time invariant systems. In time domain, you have your impulse response, your input signal x of t, and your output signal y of t, which are related using the convolution. Okay? And in frequency domain, you have your transfer function or frequency response, and you have your signal x of t in frequency domain, and your signal y of t, y of omega, in frequency domain, which is basically x of omega multiplied with h of omega. Okay, so in questions involving linear time invariant system, because now you know the Fourier transform, if I give you the input signal x of t, the output signal y of t, you should be able to give me the the frequency, the impulse response. Sorry. The impulse response. And the way you do it, you convert everything first to, because here I've given you y of t, I've given you these two. I've given you y of t and x of t, and I've asked you what is this. Okay? You can't do it in time domain, okay? You can't do the inverse convolution in time domain. But what you can do, you can convert things into frequency domain. Then you know this in frequency domain, you know this in frequency domain, and you want to find the transfer function. And you do that by doing a division, and then you convert things back into time domain. Okay, then you know this. Okay, so you convert here. When you convert here, you know these two, and because you know these two, h of omega basically becomes your x of your y of omega divided by x of omega. So you do this division, you calculate this, then you take the inverse Fourier transform, and you get that. Okay, and when I say you take the Fourier transform and the inverse Fourier transform, translate it into looking up the table. Okay.
Is it possible you can give us the opposite of that in frequency domain, where you can't inverse?
Yeah, I can. I mean, I can give you any combination of this. And the other question that I could give you is the regular, the same old question. I give you the input signal and the h of t. Okay. But the thing is, x of t and h of t are so complex that doing the convolution is not easy. So what you do is you convert them first into frequency domain, okay? And when but you can use the table lookup to convert them easily to frequency domain. In that case, you know x of omega and you know h of omega, and you want to find this. You basically multiply them, you get your y of t, you convert it back into time. Okay? Yes?
Can you do an example of that?
Yes. Actually I've done already some examples in the lectures, so I'm going to go over those examples. Okay? Also, one last thing I want to mention, so there could be a third case when I've given you the h of t, y of t, and I ask you what is x of t. Again, you can use conversions to calculate. So I think it was lecture 16. No, it was lecture 15. Okay, so lecture 15, guys, the ones that I posted online, has all these examples. Okay, has all these examples. From the Fourier series, and these are basically the properties of Fourier series. The linearity property that I told you, which is important. By linearity property, I've done this. I've converted this complex signal into these smaller versions of Fourier transform. And these ones, again, I use the table lookup for example, for this one, you can go to slide 9, which is posted, and the first line represents this basically. You can convert this to this, and the cosine of 3t u of t, you can convert it to this, and there's also this little term at the end, okay? And then there is the last one, which is this one, sine of 3t u of t, which translates into this. And all of these I've done is using that table lookup, okay? So up to here, I haven't done anything extraordinary. The only thing I've used was this linearity property. Okay? And once you do that, you can simplify it a bit, and this would be your signal in frequency. Yes? Sorry? Slide 15. Lecture 15. Lecture 15 slides, I don't know the slide numbers, but lecture 15. Okay? So here's an example where I give you the signal x of t and the signal y of t, and I ask you what is the impulse response. Okay? So I give you the input signal, and I've given you the output signal, and I've asked you what is the impulse response, h of t. So I've given you x of t, y of t, I asked you what is h of t. So the way you do it, like I said here, so I've given you in that example, what I've done is I've given you y of t, I've given you x of t, and I've asked you to do give me h of t. Okay? And the way you do it is you do conversion, you do Fourier transforms from here to here and from here to here. Okay? And once you do those Fourier transforms, Okay? So here's where I do the Fourier transform. So I take the Fourier transform of x of t, okay? And using, again, the slides, I look up in the slides, I get this, okay? As the x of omega, x in frequency domain. Then I look at the y of t, okay, and I take the Fourier series of y of t, and for y of t, here's a little trick, okay? I use the slide number 9 plus the shifting property. So here, if you want to see an example where I use the shifting property, you can look it up here, okay? And if you look in shifting property, here I have a time shift of 4. It's e to the minus 2 t minus 4, and u of t minus 4. So I have a time shift of 4, and because of that, I add this factor e to the minus j for omega, okay? So it's this guy here, and I treat this as e to the minus 2t and ut without the shift of 4, okay? And when I do that, I look up the Fourier transform, and this is the value I get. Okay? And the last step is that h of omega in frequency domain is equal to y of omega divided by x of omega. So I do the division, and when I divide these two terms cancel out, and all I get is 3 e to the minus j for omega. Okay? And the last part is because I have my transfer function or frequency response in frequency domain, and I've asked for the impulse response, which is this in time domain. I have to take the inverse Fourier transform of the transfer function, okay, which is here, and basically, again, the way you take the inverse, you do the table lookup, but instead of looking at the time domain, you look at the frequency domain. You find this, something similar to this in frequency domain, and you convert it into time domain. And when I do the conversion, I get h of t, 3 delta of t minus 4. Again, here I've used the shifting property, but the frequency shifting property. Oh, sorry, the time shifting property. Okay? So any questions? No? Okay. So the last example, I think, yeah, there was one last example for this set of slides. And in this example, in the last example, the way it works is I've given you the h of t, and I've given you the x of t, I believe. Yeah, I've given you the h of t, and I've given you the x of t. So you know this, and I've asked you what is y of t. Okay? So you can see the h of t that I've given you is this, and the x of t that I've given you is this. Okay? So you can either do the convolution integral, which is difficult, okay? Or you could convert this into frequency domain, and you can see I've converted my h of t into transfer function or frequency response, or basically in frequency domain, and it's basically this term. And I've also converted my x of t, which is a simple cosine of t, into frequency domain. And in frequency domain, instead of doing the convolution, I do the multiplication. Okay? Yeah.
You have h of w equals to minus 2 bracket 2 plus j w. Where did you get that from?
Oh, this you mean on the top?
No, the one next to it. Yeah, next to it.
This one?
Yeah.
Okay. So this one I got from these, okay? So this was the original function, right? So the way I did it is that because of this linearity property, I can take the inverse Fourier transform of this, right, separately, which is this, and in Fourier transform of this separately, right? And you basically do a table lookup. You look up in your table, and if you look up in your table, you have something like this in your table. You have, maybe I should have brought that table with me, because so you have e to the minus 2. So in your, let me write what you have in your table. In your table, you have something like e to the minus a u of t. okay? And it goes to, like, this is the time domain representation. The frequency domain representation of this is, I believe it's 1 over A minus J omega, or I omega. I think it's a plus. It's A plus J omega, okay? So you basically go to your table, you find this, something like this in your time domain, okay? And you look what the value for that is in frequency domain, okay? The only thing is, like I said in previous example, there might be some tricks involved, okay? The tricks involved are basically the shifting properties, okay? Which I'm gonna actually, maybe it's a good idea if I go over this with one complete example. So that's what I'll do, okay? So after I finish the slides, I'll go over this through one complete example.
What property is that? Time shifting?
Time shifting, yeah. This one is not time shifting.
Frequency shifting, right?
No, this one is not time shifting.
What is that one?
This one is just a regular table lookup. Okay, so if you look up your Fourier transform tables, you see this e to the minus a u of t. Okay, and in this particular example, I have e to the minus 2t. Okay, so wherever you see a, you substitute 2. So this should translate into, this should translate into 1 over 2 plus j omega, or I omega.
But
Yeah.
I knew how to do that. I just didn't know where you got the 2 plus JW in the bracket from, because I thought it would be like minus 2.
This
plus,
one?
Yeah.
Okay, so what I've done, it's minus 2 plus this.
Yeah.
So I try to add those two together. So basically, okay, I see your question. Let me do that then. So when I do that, I have this minus 2 plus 5 times, or let me just write it like this. 5 over 2 plus j omega, right? It's like that. And what I do is I take the common denominator, so this becomes 2 plus j omega, okay? And it would be minus 2 times 2 plus j omega plus 5. Okay? Which is basically this. The only mistake I've made, or the typo that's in there, is this plus sign. So here, the plus sign, I've forgotten to put the plus sign. So going from here to here, there is a typo. There should be a plus sign. Okay, but that's essentially what I've done. I've tried to basically simplify this a bit further. That's all.
Do you have to do that?
Sometimes you do, because if you want to take, for example, the inverse Fourier series of this, you might have to simplify it. Okay, and in this particular example, because I'm trying to multiply this with x of t, it's better that this is in its most compact form. Instead of multiplying this whole thing with x of t, I just multiply this with x of t. Okay? So I'll go through one example of these actually in details. And maybe I'll go through example 3. I'll go through example 3 because it has some extra stuff, like shifting property and stuff. I'll go through this example. So just remind me to go over it, okay, if I forget. So that's basically it, I guess, for Fourier series and Fourier transform. Like I said, for Fourier series, Fourier transform, guys, you had only one assignment, okay? So that should, and also this basically lecture slide where I solve the examples. So this should basically tell you where the bulk of questions are gonna come from, okay? And if you work through these examples and also the examples on the assignment and the quiz, I think you should be good. Okay? I think you should be good. So I'm very worried about the final because I don't know whether I've made it too easy or not, because your marks, your average
it's good, it's
is
good.
already too high.
No, we're working hard for it.
The class average is like 73. I mean,
That's good. That's horrible. It should be 83.
That's what I was just thinking.
I know.
yeah, 83, and then they're gonna fire me.
No, we won't let them fire you.
Yeah.
Course evaluation should help them with that.